All right, guys, welcome to the 47th WebPerf meetup. This is Making Wikimedia Fast with Ori Livna and Aaron Schultz. I'm sorry if I mispronounced that at all. So just quickly, I wanted to thank our sponsors. Thank you, Wikimedia, for hosting us. This is a really wonderful space. Thanks for providing the food. And just a quick note, O'Reilly Velocity Conference is coming up in June. If you guys haven't registered but you're really interested in web performance, I highly encourage that you check it out. We have a 20% coupon code, so if you enter SFWPMU20, you can get 20% off your Velocity tickets, so definitely check that out. We also have a coupon code, as always, for any books that you get from Velocity. You can save 40% on printed titles, 50% on ebooks. Enter coupon code DSUG. You can follow us on Twitter. We're SFWebPerf. And if you tweet about this event tonight, please use hashtag SFWebPerf. We've got another meetup coming up, so definitely mark your calendars for number 48 with Alwa Reitbauer. And I probably messed up that name, but check out the meetup group page and RSVP. And with that, I'd like to introduce Aaron. No? Ori? Ori first? Sorry. Oh, sorry.
I'll introduce them both. So hi, I'm Rob Lamphere. I'm the manager for the platform engineering team here at Wikimedia Foundation. I just wanted to give a little bit of background. So Wikimedia Foundation, we're the nonprofit that hosts a lot of collaboratively edited sites, including we host Wikipedia. And so we're a top 10 website, which gets a lot of traffic, and therefore we have lots of performance concerns. And so two of the speakers, both of our speakers tonight, Ori Livna and Aaron Schultz, both are senior performance engineers here, and they're going to talk about some of the challenges that they've had and some of the solutions that they've come up with for this. Before we get started, though, I just wanted to get a sense of the room here. How many people, is this their first time here at Wikimedia, either for a meetup or anything like that? Okay, so how many people have been here before? Just a handful. Yeah, we've had some meetups. We do have meetups every 3 months or so that are focused on Wikimedia-focused things, and so we encourage you to join our meetup group as well, and see when we host other things here as well. So with that, I'm going to start off with Aaron Schultz, our senior performance engineer.
Hello? All right, can you hear me? All right, I think this is pretty good. So yeah, I'm one of the senior performance engineers. Ori is the other one. So, there's two of them. There's two of us. Yeah. So one thing I want to be clear on, we're still doing announcements, right? Of introductions, instead of getting into my slides. All right, then. There we go. Yeah, I usually use Debian, not. All right. So before I start into this, just a little bit about myself. I've pretty much been working at Wikimedia for 6 years. I was a contractor before, and then I was full-time actually at the office for about 2 years. I've always sort of worked on performance-related things, at least after the first year or so. I've always found that interesting, and I've sort of gravitated towards that over time. So this whole role of senior performance engineer, I wasn't even in until the last few months, and it didn't really even exist that long before then. So yeah, I'm definitely very enthusiastic about this stuff, and I don't know, let's dig in. So what I want to start off with is basically what I'm going to talk about is the sort of 3 mile distance view of like our architecture and how everything's set up. And then I'll talk about some specific caching and backend problems. Hopefully I'm trying to focus on things where like the techniques might be generalizable. So like you could, carry some of the stuff over, possibly reuse some of the code or at least some of the ideas. So like hopefully the stuff isn't too specific to the problems that we have. So for our architecture, what we essentially have is Varnish in front of everything. There's 3 different data centers. And then like hopefully that's what you get served by. But if not, it's going to fall back to other systems in order to render the content. So for HTML pages, it's like you go to an article, right? Okay, you hit Varnish. If it's not there, it goes to the Apaches. Assets like CSS and JavaScript, they're not in Varnish. They go to load.php, an entry point of MediaWiki. And the same with, you could basically follow this down the line. More interesting is thumbnails, which if they're not already in our storage, which we call Swift, we actually generate them on the fly, put them there, and then return it so it's there next time. And I'll look at, to make this a little bit easier to see, the next slide I'll have a diagram of how these parts are laid out. We also have job runners in the background. There's about 16 of them. And we have our API servers, which they run MediaWiki. It's just another entry point. Historically, there's been this division of, the APIs for bots and basically just bots, and then the rest of the site is for everything else. And so we split off the Apache servers for those, which is useful since if a bot is spamming a certain query and it starts to make the site slow down, or maybe something becomes unavailable, which doesn't happen that often, but if it does, it means it's mostly isolated to the API. So like the regular UI and everything basically still works. It's kind of in the future we'll have to be more nuanced because, more and more editors are just making their own little GUIs that use the API, and there's OAuth, and there's all these tools, and there's, our visual editor, which uses the API, so the distinction isn't probably going to be terribly useful in the future, but it's a useful separation to have now. And so here's this diagram that I was talking about, which basically just enumerates what I was saying in a more clear way. This was it's mostly accurate, and this is by Ryan Lane in a previous presentation like a year ago. The only thing that's a little different is I think that squid there should be Varnish, and we don't use Ceph anymore. We tried it, and it didn't work well enough. But otherwise, that's a pretty up-to-date diagram. It's basically how our architecture still is. So as I said, we like to put Varnish in front of everything, because Varnish is really fast. And the main thing is like you want to serve from the edge. So like there's no way to really beat the speed of light. So you just have to have a CDN that's physically closer to people. So we have one in ESOMs, for Europe, ULSFO, which was set up fairly recently, and that serves like the West Coast, parts of Asia, and then we have what we call Ekiad, which is our data center in Ashburn, Virginia, which also has caching centers. So in order for this to work, you have to have predictable URLs. Like, you can't have a site where like every URL is just like this has all these weird parameters in it that are like specific to the user and has all these settings or customizations or skin types. Like if you do that, then your cache will get really fragmented. So our approach, at least for logged out users, is to try to funnel them into like, one URL per page. So like if somebody's visiting the page hello, like that's probably the URL they're visiting it from. There are other URLs that will access the same content, but we don't cache those, and we don't point anyone to those. So if you do a Google search or whatever, like you're going to see hello, you're going to click it, that's where it's going to take you. For some languages, it's slightly more complicated. So like for Chinese, there's a lot of variants of Chinese. So like we have like 6 different variants we support. And so people might want to view the article with a slightly different interface, a different variant of Chinese. And so, okay, if we know there's exactly 6, we give that simple, almost REST style URL, very simple, standard. And like we can enumerate it. So when we need to change a page, if somebody edits the article, we know exactly what URLs to purge. It's a very small, bounded, finite number. So like for URLs with like, if you're saying I want, this old version of the article of hello as it was at some point in the past, like we don't cache that. Like, it's just not worth caching. It would just, like the odds of a bunch of people viewing that same old version of that article is kind of slim. So like putting that in a cache would just fill the cache up with garbage. So there are some clever tricks we use. So like if you have a, different browsers sometimes encode URLs differently. Like that's slightly annoying, but like you can, especially if you're following links or whatnot. But I mean, you could work around it in VCL. So if you see a URL with this sort of non-canonical encoding, there's a lot of different combinations. Like if you recognize it, you could rewrite it to the canonical form internally in Varnish and VCL. This happens both on purges and on gets. So basically, what happens is that when if you're using this old browser and you're using this, you're accessing the page to the strange URL, which actually is fairly common. Like it's not some rare edge case that doesn't happen to anybody. What happens is that you get a cache hit just like any other page, and that's just it works and that's fast. And that's the alternative would be something like maybe whenever you have a non-canonical form, you redirect to the canonical form, which works and deals with cache invalidation, except that adds extra latency because you're basically telling the person's browser to then come back again, and request the second URL. And in some cases, it might not work at all because I might get stuck in a loop if they're suffer the same problem. And yeah, if you are doing the redirection strategy, you can set a TTL on the redirect, so at least Varnish will cache that. But you try to avoid that. Another trick that we use is that if we have like banners or something, like if you want to, say it's fundraising time and you want to have a banner that says donate, like you want that to show on like, maybe every page for all your users or every page for some users. And you want that to be relatively, immediate. So if you just put the actual HTML of that banner in the page, like there'd be a lot of problems with that approach. Like since we cache all the pages for 30 days in Varnish, like you would have to somehow purge all the cache and then have them with the new version, with the banner, and then sometimes you want banners with randomized content or where it depends on where the user is, and that you need some way to get around that. So what you can do is you could give JavaScript, which could be the same JavaScript to everyone. You could cache that, and then that JavaScript can then do the randomization, the bucketing. It could use cookies, whatever tricks it wants, and then it could add these notices dynamically, and you don't have this cache fragmentation problem. And particularly interesting is when you want to have a banner or whatever it is vary based on somebody's location. Like again, the easy thing to do would just be to go back to the back end, set a cookie or something. The problem with that is that, again, if you don't have this cookie, like a lot of people, the first time they view, a Wikimedia project in a while, like that's extra latency. They have to go to the back end. Like you'd want to stay on the edge. So you can do that if you actually do the GeoIP lookup, like in Varnish, which you could do in VCL. And in fact, I'm probably not going to show this code, but you could, follow this link, and hopefully this slide will be public somewhere. So basically, it's just inline C, this is what makes Varnish really powerful is VCL. Like not only can you do a lot of things in it, but you could also then, without using C, but you could also use inline C. And that's just how this encoding rewrite worked that I was talking about before. And that's how this GeoIP stuff works. And again, staying on the subject of the edge, another thing is, assets, CSS, JavaScript. Like an easy thing to do is to just have like, 20 different, script and style sheet tags with their own SRCs. And I get that works, but like it's kind of slow. I mean, like for one reason, browsers, they'll try and pipeline, but they only have like 6 connections. So if you have to load like 30 different things, like a lot of that's going to serialize and it's going to be slow. So if you could like bundle them together, load a bunch of different JavaScript modules all at once, it's faster. So you have the convenience of writing all these modules as independent things in the code, But when users get served the HTML, they're told to request load.php, get all this JavaScript, get all the CSS for multiple modules at once. In order to do this, you need like a proper dependency management system. And that's, for MediaWiki, that's called Resource Loader. That was written a few years back. And another cool thing that Resource Loader does is, for the developer, they could have, they could have some CSS that has a background that has a URL attribute that points to some file, and like that's easy to do, whatever. But then Resource Loader can then automatically, look at that CSS and then say, okay, this image could actually just go inline, so let me just automatically convert it to a data URI, and then that'll get served with the CSS bundle. And so again, that cuts down the number of round trips you have to make. Even though they're to the edge, like it's a bunch of round trips is still going to slow you down. Another thing, which is again very useful to any CDN in general, is just like Stampedes. Like if I update a page, say an article, like Barack Obama or something, I issue a purge because it's updated. The content in Varnish is stale, it needs to be changed. Like you don't want to have like immediately like 50 users come in and then have like 50 Apaches like sitting there, rendering that article. And the same with thumbnails. If you change a file, all its thumbnails, are outdated, so you need to get rid of those ones. And it's a similar problem. So Varnish helps a lot with this. Like literally right out of the box, if you use Varnish, it will do this kind of logic. Or like, once the server, if you're using like Carp or whatever it is, even if you're not, whatever the server is that's responsible for a certain URL, when it's sitting there and it gets a request and then more come in, like it's not going to like send separate requests to the backend like all at once. Like all the other ones are going to wait on the first one. So hopefully they could just, the Varnish server gets a response and it can just spit it back out. And that avoids overloading the backend. If you're not using Varnish but you're using Squid, you have to actually enable this, which it's a feature called collapsed forwarding. And it's the exact same idea. Almost a related thing is, again, another one of these tricks is that if you are using Carp, you'll have like, if anyone's familiar with that caching array routing protocol, if you're using Varnish, it is a thing that basically works like that, which is what we use. You're going to have a bunch of Varnish servers. When a user comes in, they're randomly going to hit one, and then that one might have the object they're looking for, but it probably won't. So it uses the consistent hash to figure out which server actually does. Then it communicates with that sibling Varnish server, which that's normally great and everything, except like sometimes you'll have a certain URL that isn't really cacheable that's accessed with a very, very high volume. And like that might, since that's all mapping to one Varnish server at some point, like that might not be the most efficient setup. And we had this problem with one of our login pages. Like everyone's, people log in, or there are certain checks to see whether you're logged in, and they're getting hit with really high frequency. And since the consistent hashing just looks at the URL, then it, that's all going to go to one server. That one server is getting overloaded. So the trick was to just NVCL, again, the power of Varnish. You just, for that request, you literally can just say, okay, use any random backend. Don't, like try and map to the specific server based on Carp. And that immediately solved the CPU problem on that one server. And in terms of like when you do fall through from the edge, okay, obviously not everything's always a cache hit. You do have some of the similar problems. So like if, for example, if a bunch of logged in users were to view, I don't know, Michael Jackson or something, after he died, which actually was a specific problem that happened. A lot of these solutions we make are in response to the site going down due to a certain problem, as you may have figured out. So it's useful to have some sort of system on the back end that can do work deduplication. And so we wrote this thing called pull counter that does exactly that. Basically you make up a key for whatever the work is, based on the article. You have to then acquire that key. And then, once you get acquired, once you actually acquired, you do the work. If you get blocked, then you'll have to, wait for whoever it was to finish, whatever process that was. Then you can reuse whatever cached output they used. Whatever cached output they stored, because they always store it somewhere. We always cache it. And there's a C daemon for this that actually does the logic of, being the server that, handles this acquisition. They're not quite locks, but you could think of them as that way. It's a sort of semaphore semantic. And that daemon you could use totally without MediaWiki. Like, it's its own little Debian package. So you could install it and use it for other things. Another thing is like just using Memcache, the add method is it's a somewhat ghetto version of the same thing, but I mean it does work. So we do that in some places too. Obviously, we use Memcache for anything that's really hard to generate, like parser output in many cases. And as I said, just like with the front end where you try and coalesce the URLs down, you also want to avoid fragmentation here on the back end. So like going back to parser output, for example, parser output is basically most of the HTML of a Wikipedia article you see. That's what the wiki text renders to. It's usually slow to generate. I mean, for example, if you try to go to World War II and press edit and then save, like it's going to take like 50 seconds. Like it might just time out sometimes. Yeah, that's pretty broken, but that is the status quo. So you don't want to have parser output get fragmented based on a bunch of stupid user preferences, which is one of the things we're trying to cut down on. So like if somebody says, oh, I want my thumbnails on pages to be a little smaller than the average size, like if you're going to support a feature like that at all, like do it as post-processing on the output. Don't like fragment the actual parser output itself. Like that's easy to do, but that's really expensive. So I mentioned Memcache already, as you can guess. But we use a lot of other things for caching. Redis, sharded MySQL for our parser cache. Basically, if the Memcache is great, but like if the power goes out or there's some problem with Memcache servers, it's nice to not have the site be totally down for like a week. So like if you could have a persistent backing of like some of these parser entries and other very, very expensive things, that's very useful. And we chose MySQL because we were familiar with it. It works. It's reasonably fast, especially on SSDs. And so we evaluated some other tools, and they like Cache, and they had some problems in theory they weren't supposed to have, but they did. So like we use MySQL for a lot of things. You're going to see that come up later. We're sort of a MySQL shop. We also use Swift, which I'll talk about that a little bit more later, but we use it for our originals, for our actual, like the full version of an upload. But we also use it for caching thumbnails instead of just generating them every time. So, if you could cache a lot of stuff in CDN, but again, at some point you're going to have to hit the back end. You're going to have to generate things. You're going to have to, read things from the database. So the approach is, if you have to use the database, then at least use a slave, right? Don't just use the master database. So use a slave whenever possible. Sometimes you need to, obviously if you need to do a write, you're going to write that to the master. But also if you're going to read something to use it for a write, like if you're moving something around, like you can't really use a slave because like, that could cause, temporary anomalies to become permanent. But when you can, you try to use a slave. Now, if you're using slaves a lot, you have to be careful about lag. So like if somebody edits a page and like somebody else looks at it a minute later and it still is the old version, like that's kind of suboptimal. So we try to avoid that kind of situation. So we basically, when we need to pick a slave, when MediaWiki running in an application server needs to pick a slave, it tries to pick one that's not lagged if possible. Otherwise, it may even wait a little bit, but at some point it'll just give up and give stale data. You don't want to have the site become unavailable because all the slaves are lagged for like 6 seconds or something. And so you accept inconsistent data in those worst case scenarios. We also do shard the databases, not horizontally, because that's, as anyone who knows about sharding would know, that's really difficult, especially if you didn't write something to be horizontally sharded to begin with. But we can shard it based on things where there's just naturally no join boundaries. So like English Wikipedia is on its own, has its own master, its own set of slaves. Commons, likewise. There's 6 other clusters with various other wikis spread out among them. And this goes a little bit back to the issue of slave lag, but this is a little bit more specific. So like users of Wikimedia sites tend to have a high expectation of consistency. So like if you specifically save a page, like you'd expect that when it reloads, did you actually see your edit? And if you come back, did you see it, right? It would be pretty hard to violate that expectation. So again, this describes a trick we use. You save, okay, you store the master position at that time in Redis. When they then view the page again, we're going to see that in their session, the last master position. Try and pick a slave that's synced to that, or wait if necessary. To a point, although like I said, if we're not going to wait like more than 5 seconds, at some point we'll just give up and give stale data. But this pretty much, like 99.999% of the time, this basically means that people see their own changes. It looks consistent. It's almost like you're reading from the master, from the user's perspective. But we're actually using a slave. Right? We're trying to do the fastest thing possible, use the slave as much as possible without it actually looking inconsistent. And so I'm going to briefly go over some database performance stuff. Obviously, use appropriate indexes. There's a lot of good articles and blogs written about this, like Percona has good blogs. The MySQL documentation is good. I mean, there's nothing beats reading that, even if it seems kind of boring. But a few things that are maybe not quite so obvious is that, when you have to when you're doing an update query or a delete or whatever, some query that's changing data, like MySQL, in order to do its locking, it's going to try and use it. It's going to try to use the indices. And so if you don't have good indices, it's hard for it to establish and lock records anywhere, at least in an efficient way. Like it might pick some index that is the best but isn't that great, or there isn't one at all, and then it'll just lock the whole table. Then that can kill concurrency. So that's something to be aware of. But you shouldn't just like add a million indexes. Like you shouldn't just use a checkbox, tool where you just like say I want an index on that. I mean, like every index should actually have to do with the query that can probably use it, or that that actually exist. If you add a bunch of extra indices, then your writes will slow down, particularly unique indexes, because if you, I don't know, depending on how much you know about MySQL internals, like, unique indices cannot use the change buffer, whereas non-unique indices can. So you definitely don't want to have a bunch of pointless unique indices. Another trick that's useful, I would say, is, again, following up on the idea of not adding a bunch of indices, is you can often reuse an existing index by having a redundant condition. So like that example is like, you have a revision, it has an ID and a timestamp, and then there's some roll-up table, recent changes, which I call RC, which has entries that are corresponding to revisions and other things. So if you want to look up a recent changes row by revision ID, like you could add an index for that, but you could also just redundantly add the timestamp into the condition, because we already indexed that, and then the query is still fast, and you don't have the overhead of an extra index. Something that's bitten us maybe a few times is an index where like the vast majority of the values are actually null. I mean, anytime you have an index that's not very selective, it's not necessarily useless, but it's not very useful. So just be careful about that. And lastly, I would say is on indices is that make sure you actually run analyze, like on a cron periodically or whatever on your database. Because if you don't, then the statistics will get really updated, and the planner will start picking the wrong indices, and you won't know why, and the site will start to slow down. So getting a little MediWiki specific, we tend to wrap everything in one transaction, for better or for worse. That's true for a request that just reads data, and for ones that just write it. I mean, the nice thing is it's obviously like, as the slide says, it's very consistent. You have that repeatable read isolation, which we run on. You don't have, if some error comes up or there's an exception, you don't have to worry about like some stuff getting written, but then the other parts that you needed to write didn't happen. But the downside is that when you're doing writes, if your whole transaction is wrapped in a database transaction, you have to make sure you're not doing anything slow in that transaction before it commits, or the lock contention starts to get suboptimal. So, the solution, and I would say you should do this in general, whether you're doing what MediaWiki's doing or not. Like, you want to keep your read transactions and your write transactions short. If you want to do a 4-hour analytics query that's running to doing all these group bys and whatever, like, try and do that on a dedicated slave and not like the primary slaves or, God forbid, master that you're using. Even though there's like multi-versioning and all that nice stuff in MySQL, there's still issues of gap blocks and old versions of rows that you can't technically delete because some old transaction's running. And both of these can be annoying things to debug because it can cause slowness in totally unrelated queries and tables that you wouldn't think would be slow. Again, you just don't want to have to deal with that problem. And as for write transactions, again, you want to keep them small and short. Like, usually, with one thing we've noticed is that if you have a lot of writes hitting the master, and we've had this happen due to bugs in the software or other reasons, the master usually doesn't fall over unless you really, really, really slam it. But what usually falls over first is the slaves. Like, they're doing serial replication in MySQL, and they just can't keep up. So they get farther and farther behind. And I mean, like, they could be minutes behind, eventually an hour behind. Like, you don't even want, like, you can't have a site where you're randomly serving data that's an hour old. So, like, keep it short. Try and change a modest number of rows in each query if possible. And going back to what I was saying about the lock contention, like, you don't want to have something that's, do something slow, such as parsing, in the middle of some transaction, after you're updated in a row, but you haven't committed yet. Like, that's a bad state to end up in. Part of what also makes this difficult is that, some places, some shops, they have their whole architecture split up into all these neat little services that, only minimally affect each other and, like SOA style, and that's nice. We don't really do that at all, so it's all one big, huge thing, which means that, like, trying to debug performance problems, or even just writing new code, it could be your own little plugin, could be a little tricky because you're trying to anticipate the performance when there's a million other things that could interact with it. So some tricks to make that a little easier is that since we use a database class for all of our database access, we could take advantage of that and add some callback methods, which basically say, right after the database commit happens, do this thing, where this thing is just a closure. It could be anything. And I'm not going to go into exact detail between these two, but basically, an example would be, say you want to move some files around. Obviously, you have to. That's not going to be terribly fast if they're fairly large and there's a decent number of them. And in our case, they're stored in Swift. So that could take a few seconds. And okay, so you do that, whatever. In that case, that sort of has to be in the database transaction for reasons I don't want to get into. But one thing that doesn't is the actual purges of the old versions of the thumbnails. So if you have a file, if you go to Commons, there's a file colon page, whatever. You upload a new version of that. You need to get rid of all the old thumbnails. And that part doesn't really have to be mixed in with the database transaction. So you could just do that right after you commit. And then instead of holding locks for like an extra 6 seconds or something, like, you're not. And if you were, you would actually see the deadlocks and things start to pile up. And then when that happens, it makes it hard for users to do anything. When half the time they do stuff that's really slow and fails and have to keep retrying. And probably lastly on database performance is if you have to debug things, I would say actually log all of the database errors, including the backtrace, like everything you called, in whatever language it may be in, PHP, whatever. you can, if there's a deadlock that keeps happening, you could do show in ODB status, which is really useful because instead of just saying the query that had the problem, with the user, that got rolled back or whatever, like it also tells you what the other query was, because a deadlock is always two things waiting on each other, and this helps tell you what the other side of it was. And MediaWiki specifically also includes a log that tries to detect this, any sort of transaction where you do some statement that creates locks, then you do something that's really slow, and you're just holding those locks forever. And then we log that, in the calls, so we can then find that code, fix it, or talk to the developer who wrote it and ask them to fix it. So moving away from databases a little bit, although we're basically talking about our text storage now, which could go on anything. I mean, it's basically all it needs is a key value store. In our case, we're kind of going back to sharded MySQL again. That's what was done in like 2003 or whatever, and we just keep using the same system. It may not be the best one, but it does work. So, like I said, we shard vertically our databases, like English Wikipedia is one, Commons is another, but that's just the core metadata. If the actual text of every article in Wikipedia and all the other sites it's kind of a lot to just put in one database. So what we actually do in the databases that store the metadata is store pointers to where the actual text is, and those just point to where in external storage, what cluster, what ID of a blob, is this text in. So it's a very ad hoc system. It's not glorious, but it works, and it's reasonably fast. For our files, as I mentioned, we use Swift. If anyone's familiar with OpenStack, actually, how many people have used like OpenStack products? Yeah. So Swift is one of their main products, which is you could use it as their storage. I think you can also use it for block storage, but we're just using it as an object store. It replaced what we used to have, which was one NFS server. Like for everything, there was just one NFS server. Which there's funny things about that. Like it would go years without getting restarted, and we would be running really old versions of the operating system. Because if in order to update it and like take it down and restart it, then all of the media would stop working. So that wasn't the best system. So now we have a distributed system. You could take out nodes, add in nodes. This could happen relatively seamlessly. Again, we try to make use of, we have 3 replicas, and we try to make use of all the replicas, just like we try to make use of all the slave servers as much as we can. We try to avoid having to hit all of them. And by that I mean, if we absolutely need the latest version, we can tell Swift, give me the latest version, in which case it's going to have to hit all of the replicas, see which one has the latest version. Obviously that's not as scalable, so we only use that if we have to. And, one of the things that's useful, I'm not going to talk about sharding, I'm just going to say that we had to do it for technical reasons. But one of the things that's also useful is, because it's an HTTP-based storage, unlike NFS, it's very easy to do concurrent operations. You just use curl multi. So back to this problem of having to purge alt thumbnails of a file when it changes, when you upload a new version, there might be like all these different size thumbnails. So you don't want to just like issue like HTTP deletes one at a time. You could just do curl multi and like delete them all at once. Very briefly, our search architecture, we went from Lucene with a bunch of ad hoc stuff on it to Elastic. Again, 3 replicas. We're not totally there yet. It isn't like we haven't actually fully done English Wikipedia yet, so that's kind of important. We have done a lot of our other projects. We've had them migrated over. So one of the things that's useful for reducing backend latency is queuing. Like there's a lot of sort of slow updates we have to do. Like a template is used on like say 50,000 pages, right? And a template's just like, if you want to have the same thing on a bunch of pages, like you have one page that's that thing, and then you use it on a bunch of different articles. The only thing is that when that template changes, then you have to go back and change all of the articles, right? So we can't really just do that like synchronously when a user presses edit. So we have to enqueue a job for that. And there are other things that maybe you could do synchronously, but like it's slower, so you don't. So like we should probably use queuing even more than we do. Like I'm a pretty huge advocate of that. Like if it doesn't have to happen synchronously, then why make it? And these are just some examples of the tasks. So another one of these sort of ad hoc systems that we have from like the 2000s is our profiling. So a lot of people have like xhprof or whatever xdebug or whatever it is you may use. We're still using our own profiler, and basically you invoke it by doing profile in when you start and profile out when you're done. It's a fairly simple system. If you are in the business of implementing your own profiler in PHP for some reason, you could use the trick that we have of see the lower example. Basically, you make an object that when you construct it does profile in, and then its destructor does profile out. So if you have like an exception or a return statement, like it just automatically profiles out, which is kind of useful. Although if you can, you should really just probably use xhprof and like not bother with this. So this profiling data actually gets, it actually goes somewhere. So it gets aggregated mostly in Graphite. We still have our old profiler report thing in Python, which is another one of those things that we made ourselves. It's useful for just tabulating, what are the top slowest things. Beyond that, it's not terribly useful. Graphite, on the other hand, is an open source tool. You could use it for whatever project, and may not have the best user interface, but it's very powerful. So you can, once you have like graph data inside of it, you can make graphs based on a time range. You can filter it to the most deviant of all the graphs. You could do integrals, derivatives, subtraction of integrals. Like you combine everything. You could do like almost whatever you want. So if you haven't used Graphite before, I would definitely recommend at least having a look at it and trying it, because it's a pretty useful tool. Monitoring is mostly standard stuff. I would say the Logstash we've set up recently, which is also kind of nice. So if you have a bunch of log entries, like you can dump them to a flat file. Like Logstash is a better system than that in some ways. Like you could put a nice Kibana front end in front of it, which is what we do. You could do the searches from the web. You could see the graph of like how the particular log or the number of entries of a log that meet a criteria have changed over time. So you could see if there's some sort of regression. So that's pretty useful. That's another thing I would recommend looking at. We do still log to our flat log files, and if you love to do crazy GNU utility commands in Bash to slice and dice it, I still do that. Like that's something that I do sometimes. I admit that that's still useful. So I wouldn't say that Logstash totally replaces this at this point. So basically, kind of wrapping this up with, in general, our strategy for anyone making some sort of extension or a new feature or whatever. Basically, we try not to worry about micro optimizations. So you shouldn't be making your code more complicated and trying to use triple equals and little things to make your for loop 10 nanoseconds faster. I mean, you should try and focus on when you're first writing your code, like focus on the basics, like the obvious things. So don't bring down the site, but also like try and design things in a way where you anticipate that it would have reasonable performance. But like you can't. It's often very difficult to anticipate where performance problems will show up, and sometimes it'll happen in the places you didn't think it would, and sometimes the areas where you're adding caching, you really didn't need it, and it wasn't that useful. So if you have like all these optimizations that might be helpful or maybe are a good idea, like it might be nice to keep them in mind. Make the code so it's easy to add them, but don't actually add them until there's some evidence in profiling graphs that actually indicate that there's a hotspot that's actually worth optimizing. If you just toss everything in Memcache, whether it's needed or not, like all that's going to do is cause it to fill up, and then it's LRU, and it'll start evicting things. And some of those will be useful things. The same with any cache, right? So, and when you start caching things, you have to worry about purging and invalidation. And if it's, it's more room for bugs and mistakes. So like, I would just say that people should, I hate to use the old adage, but premature optimization is the root of all evil. And so we try not to, optimize prematurely. But there's always that tension of like, on the one hand, you should try to reasonably anticipate the performance and not bring down the site with your new extension. But on the other hand, like, you can't always know exactly where the problems are going to show up. All right. That is the end of essentially the end of the slides for this presentation. So yeah, I think I should probably turn it over to Ori. I don't know. How am I doing on time? I'm like way over.
Does anybody have any questions for Aaron, though? Can you do that really quickly?
And I should note, there is like a Q&A after all this, right?
Oh,
Or is it? You could probably just do it whenever, as long as people are gone by 9-ish, whatever.
yeah, let's do questions now.
Better,
Here.
Can you talk a little bit about your experiences with Ceph? You said that you actually stopped using it and replaced it with Swift.
Right.
Can you tell why?
So, first, let me tell you the reason why we tried Ceph. So we started with Swift, then we were trying both in parallel, which was kind of interesting. So the reason we wanted to try Ceph is because we had a lot of problems with Swift. Like I alluded to the fact that we had to shard the containers. And the reason we had to do that is because they're stored in SQLite databases, which, if you know anything about that, you'll know that the concurrency of SQLite is like 0. So like, it's kind of odd that was in a distributed system that's supposed to be scalable. But that was just one problem. Like, just architecturally, Ceph is actually superior, right? It's more of a distributed system in a proper sense, whereas Swift is in some ways kind of a bag of scripts in many areas. The problem with Ceph is that it's essentially just bugs, and part of it's from the fact that we use Ceph in a way that a lot of the people, like on DreamHost, don't. So like a lot of people, when they use Ceph, they'll just store immutable objects, and then they don't change them. Whereas like we do deletes and moves and all that. Well, moves are just copies and deletes. We do all that stuff. And that exposes certain bugs and like the replication. A lot of these things were fixed. We had a guy named Faden. He still works there. He's actually also a Debian contributor. He's a really awesome guy if you've ever met him. Who is basically working with upstream, Inktank, who is the people who make Ceph, making very detailed bug reports. And there are just numerous bugs and issues we kept running into. Or a lot of them would cause Ceph to sort of panic and go into sort of downtime or get really slow, and it would start scrubbing all of its files to check whether they're consistent when there's not actually a problem. And so it was less stable than Swift for our use case, and even less stable than the one NFS server that we had before. So not to knock Ceph, I mean, it's definitely an improving product. So yeah, that's essentially, I mean, I could get into more details maybe afterwards, but it's mostly just bugs. It's not actual architectural problems. Architecturally, like most of us agree that Ceph is better than Swift.
Awesome. Since we're running out of time a little bit right now, Ori's going to go, and then we'll do questions at the end, so people that need to leave can leave, and people that want to stay for questions can stay. So thanks, Aaron.
Yeah, that makes sense.
Nice.
Right. I am not plugged in. Okay. So this is not grabbing it. I am recovering from a cold, and I'm hopped up on cold medication, so this is going to have like a slightly hallucinated Hunter S. Thompson quality. I can't do without my slides, Chip. I'm gonna cry.
Yeah. How would I say yeah, how would I say employed if we didn't have that?
Okay.
Let's see. It'll work. Hold on. There we go. Okay.
Sweet. Okay, that is a big globe made of puzzle pieces. Yeah, so I'm Ori. Can I take this out? Okay. I'm going to sing. Yeah, maybe I'll do that. Thanks. Also a performance engineer. What I wanted to talk a little bit about today is give you a sense of how performance engineering at the Wikimedia Foundation is a little bit unique and different, and just some of the interesting things we've done around performance and how we've been thinking about it. So start with a big claim, which is that performance is the biggest problem facing Wikipedia today. And I should, if there are any sort of diehard Wikipedians in the audience, I should clarify from the outset that I use Wikipedia as a slightly inaccurate but convenient shorthand for the set of Wikimedia projects that, the set of Wikimedia wikis that we host. That sort of altogether represent a cohesive movement in many ways. So what do I mean by that? It's sort of almost canonical for us to bring up this particular graph, which looks at active editors on English Wikipedia, and you can think of this image as sort of like the wallpaper of our mental desktop, in that it gives a sense of urgency and context to practically everything that we do. And so you might sort of wonder, and this coincidentally is sort of how I got involved with working here. I remember I came to visit, sort of unsure about what I was even coming in for, and I got into a really animated discussion about this exact graph. And so it remains for me the kind of context for my work. And if you think about how this relates to performance, the sort of immediate thing that comes to mind is, I'm sure you're sort of all intimately aware of the wealth of data that exists about user engagement and how it correlates with site performance. But that's actually kind of like a I'd like to sort of try expanding this notion of performance and do something a little bit richer and hopefully sensible. So the word wiki, I'm not sure how many of you knew this before. I didn't know this until embarrassingly recently. Means quick in Hawaiian, and wiki means very quick in Hawaiian. I got to thinking about what this means, and the initial implementation of a wiki by Ward Cunningham was a piece of software called WikiWeb that was written in Perl, and it was, moderately efficient. But the more I thought about it, the more I realized that when Ward Cunningham called WikiWeb quick, I don't think that he was making a statement about the performance characteristics of the underlying code, but rather about something richer. And I got to thinking about what quick means. So I actually emailed him and asked him what notion of quick he had in mind when he decided to call wikis wikis. And his answer was that it was an ability to preserve task focus and a kind of immediacy and directness with which you can manipulate content, and how that was startling and surprising relative to the workflow that he was used to, which is, you update a page by having a document that you save, and then you open up your FTP client and you upload it, and so on. There's just something inspiringly and novel about just sort of directly translating your intent into action. And it's this notion of quickness that I think we have to recapture if we are going to reverse the trend that the graph that you looked at a moment ago was showing. Yeah, so the historic definition, if you look at the etymology of the word quick, it actually comes from the Latin for living, alive, living, and animate. Yeah, so when I got to thinking about whether we are living up to this particular standard of quickness or performance, I figured that we have a scalability problem. The first scalability problem is that there are 2 of us performance engineers and 20 billion page views every month. And that is actually a great line for parties, but doesn't capture what I think is the real scalability challenge for us. And the real scalability challenge for us stems from the fact that, wikis are social software, and social software is not the same as social networking software, but rather it's software that is responsive to human ends and that is adaptive according to social needs. And yes, so wikis support collaboration and adapt to human needs. And as you might imagine, this places certain stresses on the system. So when you have a software stack that's supposed to work in 281 languages and serve diverse needs as powering sort of, encyclopedic content, but also dictionaries and maps and all sorts of structured data, you can imagine that it poses quite a lot of stress on the kind of architectural coherence of the system. And that sort of, I'm sure all of you have had the experience that making high impact performance changes requires having a clear and concise architecture that you can refactor extensively without worrying about side effects and action at a distance happening on a kind of large software set, and we have that. I mean, I think I sort of wear it with pride because I think it's indicative of the tremendous success that the software stack has had at kind of evolving and meeting the needs of such a gigantic base of users. But it does mean, as Aaron mentioned earlier, that sometimes it can be very difficult to make very broad changes in the system. And that's actually, yeah, if you look at Ward Cunningham's early writings on wikis, one of the things he said was simple things should be simple, complex things should be possible. And I think that everybody loves the first part, but it's the second part that it's difficult to sort of assess the cost of that over like a decade's worth of software development. So the realizations that come from that and that come from realizing that for me were that you can't fix every problem. And you have to practice performance engineering in the large. And what this means is, I'll go into a little bit what this means, but yeah. Yeah. So I'll give an example of this in the context of gadgets and site CSS and JS. So one of the things that makes us unique and probably criminally insane is that we let actually quite a wide range of users customize JavaScript and CSS of the site. Now, when I say customize JavaScript and CSS, I don't just mean for their account. I mean for everyone, as in changing the default JavaScript and CSS payload of the site. You might imagine that that can be problematic when you have 884 wikis, I believe. And it poses a tremendous challenge because you can't really have a particularly good grip of all the code that's that the front end of the site is running at any given time. So I'll give an example of how we approach this. So if you go to any Wikipedia article, and sorry, I'll put this down for a sec. And you open the JavaScript console, you can type MW loader inspect, and what you'll get back is, so Aaron mentioned earlier that we have a subsystem of MediaWiki called Resource Loader, which is actually responsible for loading different modules. It's not entirely CommonJS compatible, but if you know the sort of CommonJS module loading standard, it's very similar to that. And so it does give us a kind of way of subdividing minified concatenated JavaScript responses into like the individual components that are actually being loaded. So this particular thing is using, I don't know if you guys have seen this, but this is only available, I think, at the moment in Chrome. I'm not even sure that it's all WebKit browsers. I think it's literally just Chrome or Blink. And it's just using console.table, which can be sort of tremendously useful. And what it shows you is it gives you a breakdown of all the modules that are loaded by size. And it also gives you a list of different CSS style sheets that have been loaded, and the percentage, and the number of selectors that were, the number and percentage of selectors that were matched against the current DOM. So it gives you a sense of whether you might be loading CSS that you don't really need. So, oops, sorry. Go back to my slide. So, yeah, this is an example of a gadget. I should have actually probably shown that earlier, but this is the feature that we were just looking at. The way that we actually determine the count of how many selectors match is pretty interesting. So my first stab at this was to try and like actually parse the style sheet, and then you sort of have this aha moment of, you know, I'm writing in JavaScript in the browser, I have access to the DOM APIs, and you can actually just, you know, get the CSS rules and use document query selector, which very conveniently lets you use CSS selector expressions against the DOM, and you can thereby determine the numbers that actually match. So that's a kind of abbreviated version of the implementation that's doing what you just saw a moment ago. And before I get to this, we have another tool called, this was really effective at actually engaging users and doing their own performance inspection. So what I found and what animated the development of this particular tool is that users often are very grumpy when performance is an issue, but they don't know that they're grumpy about performance. It's simply that the increase in latency makes them sort of hypersensitive and hyper-irritated by different bits of functionality in the UI. And as a kind of takeaway from this talk, one of the things I'd like to impress upon you is if you see users being sort of like unreasonably cranky about a particular feature and giving sort of like a very wide range of complaints about it, and you have a hard time understanding why, in my experience, there's often a kind of underlying performance issue. And so I really wanted to sort of tap into the sort of incredible energy that our users have by channeling it into sort of more constructive direction than just sort of angry ranting, by actually sort of empowering them to inspect front-end performance and be able to sort of substantiate performance complaints with concrete data. And it was pretty successful. I think, you know, one of our users actually started a tracking bug in Bugzilla, or bug tracker, for performance issues that have been identified by this. One of the other things that we've done to sort of cope with this, actually I'm not going to demo this because I don't think I have enough time, but a tool called MWgrep, which lets you basically, so Aaron mentioned earlier that we have Elasticsearch indexing the content of all of our wikis, or almost all of our wikis, and JavaScript, user-customized JavaScript and CSS code is actually on wiki content. So when I say that Elasticsearch is indexing all of this content, what this means by implication is that Elasticsearch is also indexing user-generated JavaScript and CSS code. So we actually have a tool called MWgrep, short for MediaWikiGrep, that lets you search through all 884 wikis and see where a particular JavaScript anti-pattern is used, or a CSS selector or something like that. And you can sort of see the effect of this. This is a graph from HTTP Archive, which tracks all sorts of interesting statistics about web performance on, I think it's the 100 most popular sites on the web, plus any URLs that you submit. And if you look at, yeah, I think we're on a pretty good trajectory in terms of driving front-end asset size down and being sort of more minimalistic about and choosy about what we load. And I'm extremely happy by this graph because I've had so little directly to do with it. It's really been driven by community developers and foundation developers and even just sort of minimally technically savvy users noticing all sorts of things. How are we doing on time? I don't want to run like wildly over. 13 after. Okay, great. The other thing I wanted to show you that leverages that leverages user base and the things that are sort of unique and interesting about wikis to bolster performance work is, how many of you are familiar with navigation timing? Okay, everyone. For those of you that aren't, there were a few hands that weren't raised. It's essentially a newish set of client-side APIs that are available in modern browsers that give you very rich data about client-side latency. So the biggest thing that's useful about it is that it gives you a sense of how your website actually performs as users experience it, which is often very different than whatever view of performance you have just by looking at you know, the metrics that your own servers are generating. But if you have any sort of substantial experience working with the data, it seems like the navigation timing spec was sort of developed by browser vendors. And it's a little bit difficult to make sense of some of the data points and to translate them into actionable insights. I hope I'm not the only person that have struggled with that. But one of the things that's been tremendously useful is that we do all of our analytic data modeling on Wiki. And this particular page that you're looking at describes the data model for the navigation timing data record that we log on our site. This is the graphical rendering of it. If I were to view the source of it, you'd see that it's just a JSON object. Like all wiki pages, it essentially has a history, and you know, there's a way of, you know, you get all of the facilities of a wiki, meaning you know, collaborative work and the ability to sort of annotate document and build out the document and understand it as a kind of evolving, yeah, as in a kind of ongoing discussion or conversation, and that's sort of helped us make sense of the data by sort of piling on expertise and figuring out different ways of slicing it. Just another tidbit that I think might be useful for people that are present here. One of the things that was really challenging about using navigation timing data is that it's implemented inconsistently on some browsers. And the W3C actually very helpfully provides a set of conformance tests that run in the browser. And you can simply take those, and they're cheap enough that you can simply execute them. They specify kind of algebraic relations between the different intervals that you're measuring, and you can simply execute them and make a successful test run be a precondition to logging data. Yeah, so that's helped us get rid of a lot of the noise. This is, again, slightly abbreviated version of the full validation logic, which also takes into consideration the data model that you saw earlier. But yeah, I found that very useful. That's a Graphite graph of the data. Skipping ahead a little bit, yeah, I wanted to sort of give another example of slightly non-traditional performance engineering work, and harking back to what I said earlier about having a somewhat expanded sense of what performance engineering actually entails. So this is the older editing interface that lets you edit wiki text, which is the markup language that we use. And this is the editing interface. This is actually the save dialog for the new sort of WYSIWYG visual editor that we've been rolling out over the past 6 months or so. And one of the things that we realized with this is, so it wasn't part of the original design to do this, but we realized that so the edit summary tab that lets you sort of type in like a quick one-sentence summary of the changes that you've made has been sort of displaced into a modal. And we realized that we could actually substantially cut down on the user experience latency of saves by actually sort of optimistically submitting the content of the edit the moment the user hits the first save prompt that pops this open. So this is a great example of a performance optimization that involves no improvement whatsoever in algorithmic efficiency, no improvement whatsoever in network throughput, but a massive improvement in user experience. I mean, it's not uncommon. You know, many editors are sort of very deliberate about writing thoughtful edit summaries, and they'll take 4, 5, 10 seconds to write them. And in many of those cases, we've cut down the user experience latency of saves from about 4 to 5 seconds to virtually none, because all that happens is when you hit save, is basically a confirmation that the edit that was already pushed to the server should in fact be committed to the database, whereas up until that point, it's sort of held in a holding area. And if the user cancels, it just gets discarded, so it's basically free. So yeah, that's an illustration of a principle I tried to sort of articulate earlier, and that's a quote from the poet Allen Ginsberg from a poem of his called Cosmopolitan Greetings. And it's notice what you notice, meaning that if you, oh man, I can't sort of explain this without making an idiot out of myself. It's too meta, If you force yourself to be explicit and to articulate what are the things that are sort of rubbing and tugging at the edges of your consciousness, you find that there's a lot of opportunities for this sort of optimization that plays on perception and that doesn't, and that can be sort of achieved almost for free, independently of the complexity of the underlying software stack. In fact, one of the best experiences I've had was I was talking to Aaron about this, and I just sort of, from the very beginning of doing work on this, just thought of this as a property of the new visual editor interface. But Aaron just said, well, we could do that here too. As soon as someone clicks on the edit summary and starts typing. So we haven't started doing that yet, but it's just, yeah, I think a good illustration of the principle. Yeah, so that is about it. Yes. So do we want to do, are we going to do combined Q&A or is?
Can you guys share that mic?
Yes.
Okay, who has a question?
Thank you. And thanks, Ori. That was really amazing. So you talked a lot about user engagement at the beginning of your presentation. It seems really clear that this type of performance improvement could have some really substantial effects. Have you looked?
Yes. Not as much. Okay. So actually, I think one of the clearest bits of analysis that we have is the work that you've done in looking at the we cache front-end assets in local storage. I know it's impolite, forgive us. And as part of analyzing the efficacy of that particular approach, we were looking at page load times, and we were also tracking how those correlate with the cardinality of the load relative to the start of data collection. So if this was the first page that you've loaded after we started logging the data, or the second or the third or the fourth. The data indicated that, a very surprising property of the data, surprising to me at least, and probably not surprising to many of you, is that page load time, I believe it was the geometric mean load time decreased as you went up the cardinality of page views. And I wasn't really sure what that is. My initial hypothesis was actually, in hindsight, laughably sort of far-fetched and overcomplicated, that it was things like Chrome adaptive optimization techniques that sort of prefetch content based on previous browsing patterns. But can anyone guess what the actual explanation is? It's just that people that have a faster experience of the site use it more. So that's one of the clearest indications of that we have. But I don't think that we have adequate data to sort of quantify the impact it has on actual editors yet. But it's definitely something that I think should be a priority.
Hi. What kind of tool do you use to do load testing?
Global traffic.
Okay.
So I mean, that's a slightly flippant answer, but I actually think when you have reliably huge traffic at all times, it becomes actually sensible not to have an elaborate simulation of it, but to simply develop a deployment process that lets you roll out code to progressively larger portion of traffic, and to give you the ability to roll it back if you notice it being problematic. I mean, that's just sort of so much easier to do, and yeah, that's just how we do it basically. I consider it a perk.
So I'm curious about your metric and the increase in correlating to page views and load time. If you noticed, or if you're filtering out people who load to background, like, you know, search engine, open a tab, then you see some relevant links inside the article you're reading, and then you flip them open. So, you know, I may be generating 15 page views, but I did them in the first 25, 30 seconds as I went into the beginning of the article and I loaded some stuff, and then maybe I closed because I found my answer early and fast.
But how would that affect load time as opposed to the page views being distributed over a longer period of time?
If you're not measuring total time on site in context, all I've done is I see large page views and long and with good load times. Great, but the utilization metric is fudged.
I'm sorry, I'm not sure I understood, but that could be a property of
Well, I
old
mean,
medication.
it's a problem that like lots of sites can potentially face. Many people have multiple tab browsers and they run many tabs. Maybe I'm unique when I use Wikipedia. I just, I open lots of background tabs as I read an article, because, reference links, things like that. So I make lots of page views, but I may never actually view the page. So when you're accepting the record into your system, do you actually filter out activity? Like, does the tab even ever come into focus?
No,
I submitted a beacon to you that you didn't get.
Well, we would be getting it. So is what you're suggesting that background tabs have different load performance characteristics because the graphics aren't actually rendered and there's a lot of work that's spared until the page is visible?
No, I was actually just curious about the statistical correlation, like the number of page views and the actual fact that there were actual eyeballs on the tab. But no, I know, but I was just curious if anybody's bothered to try or if it's something that you see. Because, I mean, the only way that you can possibly see that is if you're making an association between the submitting the submitter and the frequency of their submissions. I mean, I'm not saying it's the best thing. I was just curious if anybody had given it any thought, because you can still have high page views and great load times, and that's wonderful, but not necessarily because of, say, time on site versus...
Yeah, time on site is definitely extremely complicated to precisely delimit because of precisely the problem that you mentioned, that someone can be looking at a page but not doing anything, and someone could be opening pages but not actually be actively engaged with the site, or at least not primarily. So definitely a useful perspective. Any other questions?
Hey, wait. So I heard you talk about Swift, and so like, are all images on Wikipedia served from Swift? Like,
yes.
yeah. Okay. Wait. So I learned the hard way. It scales to about 1 million objects until it like gets sucky. So like, how many pictures are there on like Wikipedia?
You mean objects per container?
Yeah. Objects per container.
Yeah, 1 or 10 million depending on the disk. But if you have SSDs, it goes a lot higher. Sorry. If you have SSDs, it goes a lot higher. And we actually, you could do the ring builder and you could set your rules to map the containers to certain, disks. The way we do our config in Puppet, like we have it so that the container servers are putting their data on SSDs, and like there's like 2 of them in each of our machines, and the other drives are just like spinning metal for the actual objects. So we're both using SSDs for our containers, and we're sharding it for the biggest 25 projects. And when you shard it, it's not. When you do both of those things, it's manageable.
Oh wait, do you know like how many pictures are there in the whole thing?
You could probably, if you go I don't know, like across all projects. I know that like the biggest one is, yeah, the biggest one is Commons. So if you go to Commons and then go to the special statistics page, it'll give you the number of images on that project. Uploaded files. It should not include deleted images, which is like half of them. Yeah. There's a few more because there's some files have multiple versions, but that's the number of files regardless of their past versions. Yeah, it's actually not that huge of a number. Like if you were to look at like Flickr or Facebook, like this is like, a drop in a bucket.
Yeah, a question about navigation timing. Is there a tool that lets me as the developer or tester view what the timing is that a user, or maybe the worst case user, is experiencing?
What we use for that is just so we stream the data that we capture via the web beacon about site performance via StatsD to Graphite, and so that's a fairly standard stack. What you get from that is, for those of you that aren't familiar with StatsD or Graphite, it's essentially a network daemon that has a very simple wire protocol for receiving metrics, where metrics are anything from timers or counters or just anything that you can quantify, and it'll compute on an ongoing basis a set of summary statistics for you. And it can write those to a graphing platform like Graphite that can let you visualize that. So I could probably pull it up after, but you can see the sort of like 90th percentile, 99th percentile, and that gives you a like the graph that I was showing earlier actually showed 75th percentile and median. But yeah, that's basically what we do. I'm not sure if you're asking if there's a way of visualizing the data on the data that's captured in a particular page session that's happening on your browser, like the metrics as they are.
Well, it'd be interesting to see the page simulated the way the user experiences it.
Oh, I see what you're saying. Oh, that's really interesting. No, but that I may steal that idea and not give you credit for it because it's really great. No, I'm joking. But it is a really good idea. That's actually really interesting.
Hi, I noticed you're using PHP. Have you guys had any performance issues with PHP, or what's your overall?
None whatsoever. It's a wonderful language with. I mean, what? Yeah.
I actually like PHP. I was just curious if you have run into any issues at all with using it or whatever. So.
Do you want to talk about that? That's probably.
Yeah, sure. So, Rasmus Lerdoff often says that the database is a bottleneck, is his universal answer to any criticism of PHP's performance, which in a way it's largely true. Like, it's very specific. Like usually with PHP, and somebody said they like PHP, actually in general like it too. It's just that there will be certain hotspots where if you're doing really heavy computation, that it's just not, it starts to become an actual serious performance problem. Like, if you're just like, if you have a API that just does some very simple stuff and you write it in PHP, it might be like 5 times slower than some other language, but it's so fast it doesn't really matter in terms of absolute time. But I think where that starts to not be adequate the most is certain hotspots, and for us that's parser. So when when Ori had the page with the edit form open and you saw the wiki text, you save, then it becomes the actual HTML that you see. Like that process of turning wiki text into HTML can be very slow, and partly that's because it's affected by user. It's in the control of users. Like users can make templates and they can make them as complicated as they want, use all kinds of conditional functions, and we can't easily control that. So like that could be the difference between a page taking 50 seconds to parse versus like 1 second. And 50 seconds in the internet, that's like you're an old man by the time it finished. So like that's not very, that's not very fast. And a lot of that, some of that's a database, but a lot of it is just like there's so much code that's happening in PHP land and various data structures and hashes. And if you look at the Zend engine, like layers of pointers and indirection and poor cache usage, like it'd be a lot. L1, L2, it would be a lot faster, something like C++, but that's a pain to write in. So like, sort of segueing into a related topic is HHVM, which some of you are probably familiar with. Actually, how many of you have heard of HHVM? Yeah, so good portion of you. So that's Facebook's answer. Like they have all this code in PHP, and it's slow at points. Even if it's not that slow, just like because it's slower, you need more servers, and when you need so many servers on the level of Facebook, like it's actually just worth it to make a JIT or something. And since it's open source and works with most PHP stuff, like we're exploring using the same thing since we may as well. And so that we're literally, I think we're testing it on one server for like job running. I mentioned we have 16 job runners. We're going to have one job runner running HHVM. That's how we'll start. If it doesn't totally break everything, and we'll then start ramping up more job runners. Eventually, we'll move on to Apaches. I mean, the goal would be that everything would just be HHVM if possible. And that could cause, like parses to be, 4, 5, sometimes more times faster than they are right now. So like if 6 seconds going to 1 is like a, pretty huge difference. 50 or 40 maybe 10 is still not great, but it's a huge improvement. It's still not, getting all the way.
Just to sort of add to that, it's true that web applications in general aren't typically CPU bound. That's kind of the exception rather than the norm. But where I find PHP poses a performance bottleneck is that it's such a horrifically designed language or undesigned language that I think it sometimes makes it unduly more difficult to do the kind of to have a kind of clear architecture that lets you kind of like pivot and make extensive changes without worrying about things breaking. It has all of the abstractions that other structured programming languages have, but the problem is that it has all of the abstractions that other programming languages have, and they're sort of not put together very consistently. That said, there's certainly a lot of truth to the kind of attitude that the differences between languages is fairly minute on the whole. I mean, we tend to sort of focus on it. Can be an expressive language. Rob made me say that.
Cool. So that's all of the time that we have for questions. Really sorry to anyone that still has questions. So let's give these guys a round of applause because they're so awesome. We still have a raffle for anyone that wants to stay for that. Here you go.
So does anybody not have a raffle ticket who wants one? There was another one somewhere. Everybody who needs one, raise your hand.